Beneath the ocean's surface, engineers are building tunnels through one of the harshest environments on Earth. These underwater pedestrian tunnels connect entire cities beneath the sea using advanced marine engineering and precision construction. From deep seabed investigations to massive immersed tunnel segments, every stage is designed to resist extreme water pressure and unstable ground conditions. The tunnel sections are built on land, sealed carefully, and lowered underwater with extraordinary accuracy. Advanced waterproofing, ventilation, and structural reinforcement systems ensure long-term safety and durability beneath the waves. This is more than infrastructure engineering. It is humanity creating pathways through the ocean itself. This is not just infrastructure, it is civilization carved beneath the waves. Every underwater tunnel begins long before excavation starts beneath the seabed. Engineers first establish a precise marine alignment capable of safely connecting two urban waterfront zones. Hydrographic surveys map underwater terrain using sonar technology to measure seabed elevations and detect obstructions. GIS data, marine traffic routes, environmental regulations, and geological conditions are integrated into building information modeling systems. The alignment must minimize structural stress, maintain safe tunnel gradients, and avoid interference with navigation corridors. This planning stage forms the technical foundation for the entire project lifecycle. Marine geotechnical investigations determine whether the seabed can safely support tunnel construction. Engineers drill boreholes from floating platforms to collect undisturbed soil and rock samples from beneath the ocean floor. Laboratory analysis evaluates shear strength, settlement behavior, permeability, and bearing capacity. These properties influence excavation methods, tunnel support systems, and waterproofing requirements. Groundwater pressure and soil instability can significantly affect structural performance during construction. Accurate geotechnical data reduces engineering uncertainty and improves long-term safety. Temporary marine infrastructure enables construction activities to operate safely and efficiently over water. Floating barges, access jetties, cranes, and batching facilities support transportation, material handling, and workforce movement. Marine logistics must function continuously despite tides, weather conditions, and navigation constraints. Construction staging areas are carefully organized to maintain productivity and reduce operational delays. Safety exclusion zones protect nearby vessels and workers during heavy lifting operations. Well-planned temporary works are essential for maintaining project schedule and construction efficiency. Cofferdams create temporary dry construction zones at underwater tunnel entry points. Interlocking steel sheet piles are driven deep into the ground to resist surrounding soil and water pressure. Dewatering pumps remove trapped water from inside the enclosure, allowing excavation below sea level. The structure must remain stable against hydrostatic forces, ground movement, and vibration loads. Engineers continuously monitor wall deflection and seepage to maintain structural safety. Cofferdams provide the controlled environment required for transitioning from land excavation into marine tunnel construction. Before tunnel installation can begin, engineers prepare the seabed through controlled dredging operations. Specialized dredgers excavate soft sediments and shape a trench matching the tunnel design profile. Positioning systems guided by GPS and sonar maintain excavation accuracy within strict tolerances. Engineers verify trench elevation continuously to ensure proper structural alignment. Sediment management is carefully controlled to reduce environmental impact on surrounding marine ecosystems. The completed trench forms the structural corridor for immersed tunnel placement. The bedding layer provides stable and uniform support beneath each tunnel segment. Geotextile membranes are installed first to prevent soil migration and maintain long-term foundation stability. Granular materials such as gravel are then placed and leveled with high precision. Proper grading ensures even load distribution along the tunnel structure. Subgrade stabilization minimizes differential settlement that could compromise tunnel alignment. This foundation system is critical for maintaining structural integrity throughout the tunnel's service life. Tunnel segments are manufactured in specialized casting yards under strictly controlled conditions. Reinforcement cages are assembled to resist bending forces, hydrostatic pressure, and long-term structural loading. High-performance concrete is poured using automated batching systems to maintain consistent material quality. Vibration removes trapped air and improves concrete density for enhanced durability. Each segment undergoes curing, dimensional verification, and waterproofing inspections before transportation. Precision fabrication ensures that every immersed section will align accurately beneath the seabed. After fabrication, tunnel segments are transported from the casting yard to the installation site using specialized barges. Careful lifting and securing procedures prevent cracking or structural deformation during transit. Marine logistics teams coordinate vessel movement based on tides, weather forecasts, and shipping traffic. Ballast systems maintain stability throughout transportation across open water. Accurate scheduling is essential because installation windows are often limited by environmental conditions. This transportation phase links precision manufacturing with offshore construction operations. Immersed tunnel placement is one of the most technically demanding stages of construction. Each tunnel segment is floated into position before being carefully lowered into the prepared trench. Ballast systems regulate buoyancy, while cranes and winches control alignment during descent. Divers and underwater positioning systems ensure precise connection with previously installed segments. Hydrostatic pressure, currents, and visibility conditions must be continuously monitored throughout placement. Even small alignment errors can compromise structural continuity and waterproof performance. Waterproofing is essential for maintaining tunnel durability beneath the ocean environment. Specialized gaskets compress between adjacent segments to create watertight seals under extreme hydrostatic pressure. Additional waterproof membranes and locking systems provide multiple layers of protection against seepage. Pressure testing verifies joint integrity before construction progresses further. Engineers inspect every connection to detect even minor leakage pathways. Reliable waterproofing systems ensure long-term structural performance and operational safety. Backfilling protects the tunnel from external environmental and operational loads. Engineers place granular and dredged materials in controlled layers above the tunnel structure. Compaction improves load distribution and minimizes long-term settlement. The protective cover shields the tunnel from ship anchors, seabed erosion, and marine currents. Final grading restores the natural seabed profile to maintain navigation safety and environmental stability. Proper backfilling significantly enhances structural protection throughout the tunnel's service life. Internal structural works transform the primary tunnel shell into a functional transportation corridor. Secondary linings improve structural resilience and create smooth interior surfaces for long-term durability. Additional reinforcement supports operational loads and protects against environmental stress. Drainage gradients are integrated into the tunnel floor to manage water collection effectively. Service corridors, cable systems, and access provisions are installed during this phase. The tunnel gradually evolves from a structural shell into an operational infrastructure system. Even fully sealed tunnels require advanced drainage systems to manage moisture and groundwater infiltration. Collection channels and perforated drainage pipes direct water toward controlled sump and pumping stations. Waterproof membranes behind the tunnel lining prevent seepage into occupied areas. Engineers carefully design drainage gradients to maintain efficient water flow without stagnation. Testing verifies the reliability of pumps, seals, and emergency backup systems. Effective drainage is critical for long-term tunnel durability and operational safety. Mechanical systems ensure the tunnel remains safe, functional, and comfortable for daily operation. Ventilation systems regulate airflow, temperature, and air quality within enclosed spaces. Electrical infrastructure powers lighting, monitoring equipment, communications, and emergency systems. Backup systems provide operational redundancy during equipment failure or power interruption. Sensors continuously monitor environmental conditions and system performance in real time. Integrated mechanical engineering is essential for maintaining long-term operational reliability. Before opening to the public, the tunnel undergoes extensive testing and commissioning procedures. Engineers verify structural integrity, waterproofing performance, and operational reliability across all systems. Ventilation, lighting, communication, and emergency response equipment are calibrated and tested under simulated conditions. Monitoring systems confirm that environmental and safety parameters meet design standards. Detailed inspections ensure compliance with engineering regulations and operational requirements. Commissioning validates that the tunnel is safe, efficient, and ready for public use. Tunnel entrances connect complex underground infrastructure with the surrounding urban environment. Architectural design balances functionality, accessibility, and visual integration with the waterfront landscape. Pedestrian ramps, elevators, and circulation pathways are designed for safe and efficient movement. Durable materials protect entrance structures from weather exposure and heavy public use. Landscaping improves environmental quality while enhancing the user experience. This phase combines civil engineering with urban planning and architectural design principles. The completed underwater pedestrian tunnel represents the successful integration of marine engineering, structural design, and urban infrastructure. Every construction stage, from seabed investigation to final commissioning, contributes to long-term safety and operational reliability. Integrated waterproofing, ventilation, drainage, and structural systems ensure sustainable performance beneath the ocean environment. The tunnel improves urban connectivity while minimizing surface transportation congestion. This project demonstrates how advanced engineering technologies can overcome complex marine construction challenges. It stands as a modern example of precision infrastructure development beneath the sea.